Hi again, welcome back. In this section, we'll discuss some of the key moments in the perceived user experience when you're loading a web page and discuss some of the factors that can cause those moments to happen later or slower than we expect. All right, so metrics are how we talk about being fast. If we say a site is fast, what do we really mean by that? What does it mean if we say a site loads in 5 seconds? It's easier to talk about page performance when we have specific metrics to measure and inspect. A page can be fast in some areas, but not in others, and different problems cause different areas to slow down. If you read performance articles these days, you'll see a lot of terminology like this tossed around. Page weight, speed index, overall load time, and so many more. These all mean specific things, but even if you know what they mean, it can be confusing to know which ones to focus on. So generally, in this section, I will hone in on 2 broad categories of metrics. First, I'll focus on the user-centric or user-perceivable metrics. And these metrics align with observable moments and subjective feelings by the user about page loading. After that, I'll cover metrics that aren't necessarily as perceivable in real time, but still come at a cost to our users. I'll start with the perceivable metrics. This is a table from Google's performance metrics articles that describes the idea of user-centric metrics really well, I think. It talks about observations or judgments that the user might make as a page is loading. And these observations may be things like, is it happening yet? Or, yes, something is happening, but is it useful to look at yet? I can see something, but is it actually useful yet? Can I use it? And then I'm using this, but is it nice to use? Is it pleasant to use? From that article, this is a timeline view of a page loading process that sort of illustrates those moments. You're going to see a lot of timelines like this as you analyze performance because they're really useful when you communicate the way a page loads to a client. Along the bottom of this timeline, you can start to see metric terms that line up with those user sentiments that I just mentioned. Metric terms like first paint and first meaningful paint and time to interactive and fully loaded. These are the user-centric metrics that I find are most noticeable and impactful to analyze and optimize for. So I'll go through each one of these and talk about some factors that cause them to be slower than we'd like. All right, so first we'll talk about time to first byte. And this is the time between when you click a link or you type in a URL in your address bar to the moment that your browser starts to receive some of the code from whatever you're requesting. So that period of time that occurs between requesting a page and getting the first byte downloaded is mostly spent on the network and on the web server, taking steps like these. First of all, making an initial request to a website by typing in whatever.com, and then from there, you go on to DNS resolution, so matching that website URL that you typed in or clicked to a IP address of the server where the code for the website actually lives. After that, you start to establish a connection with the server. And from there, we move on to securing that connection with the server, hopefully at least. That's an optional step, but it's definitely a recommended step. And then after that, you might have some redirects, for example, from a root directory to www, things like that. And after that, you get the response. And that's when the bytes start to stream into the browser. So these steps are spent as a back and forth on the network between the browser and the server. And that time spent on the network is really variable because network quality and congestion varies. In the early web days, we used to think about bandwidth as our biggest web problem. Our connection type just didn't have the bandwidth to download much at a time. Nowadays, the problem is more mixed. In 2012, Ilya Gregorek wrote this great post saying that it turns out that the web's performance problems have more to do with latency than they do with bandwidth. And what Ilya is referring to is the physical distance that our code needs to travel between the server and the browser. A trip to the server and back takes measurable time. Our code races around the world over fiber wire, but even at nearly the speed of light, that distance between computers takes time. So this is why CDNs matter, because no matter what you're requesting, you still have to factor in those proximity delays. It helps to be closer to the server that actually is returning the code to your computer. Round trips to the server can be hundreds of milliseconds at best, or often even over a second. And as web designers and developers, it's often out of our hands. But the more distributed our code is around the world, the better chances we have of a quick arrival. So, for example, if you're crossing an ocean for each round trip, you can count on adding at least another 100 milliseconds to that segment of the trip. So these add up. It pays to have your code distributed throughout the world. Here's a more local example. This is a screenshot from an audit I worked on for a US-based client where we recorded the ping times to their server from different locations in the US. And you can see even within the US, these differences in proximity are pretty apparent. See how their time to first byte varies by city to city? These are physical differences and distances from the servers. And I believe in this case, their server was on the East Coast, so you can see longer times when we were requesting code from the West Coast. So these are measurable and observable things. And the things that factor in here are latency, connection speed, and server timing. And by the way, you can check that sort of ping timing really easily. If you pop open a terminal on a Mac, for example, you can type the word ping followed by any URL that you want. So at home in Florida, I can ping the Filament Group server, which happens to be hosted in one place right now, not distributed, so it's in New York. And on average, each trip here was almost 90 milliseconds. Now that's on a pretty good connection. These increase a lot on mobile connections. So try 300 milliseconds to a little more than that if you're on a 3G connection. So network time contributes a lot to the initial connection speed and first bytes arriving. But in addition to network time, time spent on the server contributes to delays in time to first byte too, in generating the response that you want to send back to the browser. Generally, serving static files will make for a better time to first byte because there will be less work for the server to do. It just asks for a static file and reads it out and sends it back to the browser. On the contrary, dynamic pages that are server generated tend to add time to first byte. So this step could involve making database queries, parsing large files, and even compiling a response using additional network calls to other sites before returning the response to the browser. Lastly, it's worth remembering that time to first byte is an ongoing metric. It doesn't just happen once, but it happens with every request that the browser makes while it's compiling a page. So each new request to another domain goes through the same multi-step. All right, so that's first byte. Moving on from that metric, we can start to think about what happens once the bytes start arriving in the browser and pixels start to paint to the screen. So our next metric is called first paint. So first paint is when we can start to think about how a response streams to the browser. I'll summarize this part with a schematic. When you first make a request to fetch a website, the server will turn around with HTML for the page that you're looking for. And to even start rendering that HTML visibly, the browser typically needs to make additional requests to the server for other important files. And that's because when the browser receives the HTML, it scans through it for references to files that it needs to go fetch before it can proceed with rendering. And it often finds references to CSS and JavaScript files. And in the case of those kinds of files, the browser will often stop rendering the page while it loads and evaluates each file. Now, this step is directly in the way of first paint. So the heavy images, the videos that are in your page are not the ones that are holding back the page from starting to visibly render. It's this stuff. And this is standard markup, but from a performance perspective, it can be a bit of an anti-pattern. And that's because each of those requests involves fully traveling to the server and back while the page is delayed from appearing visibly. And even at the speed of light, again, that time starts to add up. Now I say, from a user perspective, when the browser already has HTML and it cannot start rendering it, it's effectively broken, even if temporarily. But once the main thread is free of those blocking requests and they come in, the browser can start to paint pixels to the screen. But those pixels in the initial paints don't necessarily have to be contentful. They can just be pixels. So that brings us to our next metric, first contentful paint. which specifically looks for content. Often, first contentful paint pairs pretty closely with initial paints, but not always. One example of when there can be a gap between initial paints and contentful paints is when custom fonts are in play. Most of web design is really about artfully arranging words. Custom typography can really elevate the user experience when it's used well, but a careless approach to loading custom fonts can introduce pain in performance. And that's because popular browsers will hide the text of the page until the desired font is fully downloaded and ready to display. And this is a good example of how a page looks when it has started to paint, but it has not fully downloaded the fonts that it needs yet. So the text is invisible. So by default, most browsers will do this nowadays for 3 seconds to give the custom font a chance to load before the text is shown in the intended font. But 3 seconds is a long time to wait on top of other delays. So this is a bit of an anti-pattern. Another factor in delaying meaningful paint is, once again, JavaScript. It's common, but not good, for sites to include external scripts throughout the HTML right where they are used. So these are ads, trackers, chat widgets, analytics. Many come into a page this way. And by default, any content that comes in after an external script, like these, will be blocked from rendering visibly until that script arrives and runs. So if you have a JavaScript file that's referenced somewhere in the body of the page, the content after it will be invisible until that file has downloaded and been evaluated by the browser. And you can see in this example, I've sort of mocked up where a script would go in red. And as soon as that script loads, you can see that the content after that script in the page source pops in. So this is really common but undesirable behavior that impacts the time to first meaningful paint. And that's what's known as a single point of failure. A script can hang for many reasons related to the network or the end server, and for a really long time. So how long will a browser just let a script hang? Well, that's a good question. Thanks for asking. I wondered the same thing, so I tested it. And many browsers will wait around 20 to 30 seconds. Some browsers wait even longer, 63 seconds in the case of Android Chrome, or up to 75 seconds in iOS. So if something happens to a third-party service and they are just not returning requests and they're just hanging, that can be pretty devastating to a page loading experience because the browser will just wait and wait and wait for that script and not show the content that comes after it in the page. And more so, that scripts call other scripts to gather data to inject into the page. So many third-party scripts end up generating many, many more requests. There's this great tool that I'll recommend that makes these graphics like you're looking at here called Request Map. And this is a request map for the New York Times website. And you can see how the third-party requests that it makes kick off other requests, and they sort of spider out. So from a meaningful paint perspective, these can sometimes block rendering depending on how they are requested. But most inconveniently, they can inject content into the page sort of haphazardly as they arrive in the loading experience, making an even longer wait for a meaningful view of the page. Here's an example of one way that a line of script can inject another script dynamically in a way that will cause page rendering to stall while the new script is requested. This uses document write. You can see document write and then a script tag. And document write is actually a really old approach that's definitely not recommended, but it's actually the reason for a lot of this mess in the first place. Document write, of course, is a method that injects HTML directly in place in the HTML. And that's a bad practice on its own because there are much better ways to insert content into the page. But it's particularly dangerous when placed in an external script because if a page is already finished loading and it loads a script that contains document write, it actually kind of behaves more like document overwrite. It'll just wipe out the whole page. And this is why browsers wait so long for scripts to load. They don't want to risk letting a script load later after the document has finished loading and have it contain document right and completely ruin the page. So they have to, unless otherwise instructed, wait for that script to load before showing anything after it. So that's a big problem we want to avoid. Another JavaScript-related issue for meaningful paint is that more and more sites are using JavaScript to populate the content of their pages after the page has already been delivered. This is kind of a default pattern in frameworks like React or Vue. Despite both frameworks, all popular frameworks, offering ways to avoid it, it's still a very common pattern. So you see a sort of skeleton of a page show up, and that's the HTML that first arrived in the browser. And then JavaScript is used to generate the content that populates that skeleton view. And we've learned in recent years that it's not safe to overly rely on JavaScript for rendering content exclusively in the browser, because it can cause huge delays in rendering, assuming it renders at all. It goes against the way browsers are designed to consume web pages. They're really highly optimized to consume HTML content that's streamed down to them. So we don't want to do this. We want to serve a page that's ready to digest right as it arrives in the browser. And we want to serve JavaScript that's small and fast so it can layer in and apply behavior quickly. While JavaScript is often the biggest culprit to these sorts of delays, images can also cause a similar delay if the contents of an image is inlined in the page using data URIs. So it's good to watch out for these if you're looking for blockers that are embedded in your HTML. They can be quite large. So those are a number of ways that first contentful paint can be delayed after initial paints. Typically, the first contentful paint marks the start of many contentful paints, and that's when you get to our next metric, which marks the largest contentful paint, which is often the most important metric to track in page loading. And it refers to the moment at which the largest contentful paint finishes rendering in the viewport. Frequently, LCP is dictated by imagery. So the largest image in a page, perhaps the hero image, as this example from Google's documentation shows, will represent the largest contentful paint element. And we can improve on this metric with images by getting images to load sooner. Another important metric to consider during these initial paints is CLS, or cumulative layout shift, which tracks the layout shifts in the page and their additive impact on how stable the layout is as it loads. Unlike prior metrics, CLS is more of a score, and 0 is good, whereas numbers above 0 start to creep into areas where you may need improvement, like 0.1 or poor when you get into the 0.25 range and up. And there are a number of things that can cause layout shifts, but most commonly, it tends to happen when images load, particularly if the images are coded in such a way that the browser doesn't know how much space to reserve for the image before it starts to load. And when it starts to load, it draws a box for the image where it will be and causes the text below the image or around the image to shift downward. And that's bad. So in future chapters, we'll look at ways to avoid that problem. But generally, those are the sorts of layout shifts that CLS is tracking. All right, so we're moving on to our next metric, which is time to interactive. And this metric represents the point at which a page is actually usable, not just looking as if it's usable. Increasingly, the reason for that delay is JavaScript. It's the time we wait as scripts are evaluated, scripts that have already been downloaded. This visualization is really great. It's from an article by Adi Osmani of Google, and the animation is by Kevin Schaaf. And this demonstrates the metric that we're talking about really well, I think. You can see the page, but you just can't interact with it yet. It's not functional yet. It looks like it's functional, but you can see the frustration here in the user trying to tap or click the page, and it's just not doing anything yet. Often this is because the page uses elements that don't do anything until JavaScript applies some behavior to them. So while that JS is being parsed, we just wait, even though it's already potentially been downloaded. Here's what HTTP Archive has to say about time to interactive. It's almost 10 seconds on average on mobile. And again, that's a median figure. So some of the most popular sites on the web are actually doing worse than that. not to pick on CNN in particular, this is a really common thing, but I ran this site through PageSpeed Insights and found that CNN takes 10 seconds on desktop, not mobile. 10 seconds to interactive on desktop. And that makes the mobile time particularly scary, a 45-second time to interactive on an average mobile device. So again, that's not anywhere near what users expect should happen when they browse the web. Again, Addy notes that we should be aiming for interactivity in under 5 seconds on a slow 3G connection on that average mobile device. So that's 5 seconds total from start to interactive. And again, we're talking about that median device, right? The one that can take 6 seconds just to parse 200 kilobytes of JavaScript that has already downloaded. So if you're using a framework for client-side JavaScript, it can be a really hard target to hit. We are shifting the burden back to the device as networks improve. We're delivering too much code. Building on TTI are some other metrics that are a little more precise when we're talking about blocking time. One of those is TBT, or total blocking time, which represents the total time that the main thread was blocked from interaction between first contentful paint and timed interactive. And another metric that just came on the scene from Google is INP, or interaction to next paint, which gives you a good idea of how long it takes for your page to respond visually to user interactions. So that's measured in real time as people use your page. According to Google, a good INP time is something like 200 milliseconds or faster, whereas a poor INP is something over 500 milliseconds. So optimizing for INP means optimizing your JavaScript to be able to execute quickly after user input. And that's similar to another metric that's been around a little while called FID, or first input delay, which measured the delay in interactivity after the first user interaction on the page. These metrics are pretty similar, so over time we may see one become more commonly used than another, but we'll have to see for now. But now that I've mentioned FID, I can talk about a broader set of metrics that I've covered already called the Core Web Vitals. And these are metrics that Google considers to be most important when looking at page performance at a glance. These three metrics even factor into ranking on Google search results now. So they've gained a lot of importance, and people are very interested in tracking these metrics across various performance tools. All right, so that was sort of a recap of the user perceivable metrics that we like to think about in the page loading experience. But there are also metrics that go beyond user perception that still matter from a performance perspective. Metrics like this deal with the amount of code that has been downloaded to the browser, and those have real costs to the user. A great example of one of these metrics that aren't necessarily perceivable visually to the user is the fully loaded metric. So this metric ends up having a lot to do with wait, because it's the point at which everything finishes loading. Everything has been delivered to the device. We used to use this fully loaded metric to describe how fast a page is, but we don't do that anymore. Now, we know that this metric happens long after a page has already become usable. And it's not really a perceivable metric, but we do see it later on our data bill. In other words, we can see it when we get a notification from our cell phone company that says our data's been used up and we're getting switched to a slower connection speed for the remainder of the month. So ironically enough, even though the visually complete metric isn't really perceivable at the time, we do end up perceiving its impact on the performance of future sites we visit, because they'll be a lot slower due to our new connection speed. And speaking of non-user perceivable metrics, the next metric, total bytes, marks the actual file size that comes along with that fully loaded metric. On mobile, the median page size for this metric is over 2 megabytes, so that adds up pretty quickly. So that's pretty much it with our metrics. From here, we can move on to learning how we use tools to analyze these metrics.